Hello sir, my name is Harikesh Patel and I have to introduction about the floating point arithmetic unit. And good morning this is the design of the 3D simulation of floating point arithmetic unit or FPU in modern computing, and adding decimal numbers like 5.75 and 2.5, and is a complex process that the CPU breaks down into a 5-stage pipeline to ensure precision and speed. I have built this XR inspired tool to visualize that internal logic. So the step 1 is when a user enters a decimal number, the system converts it into a 12-bit binary representation based on the IEEE 754 standard. As you can see on the screen, the bits are color coded: red for the sign bit and blue for the 5-bit exponent, and green for the 6-bit mantissa. This decomposition is essential because computers process these components separately. Then after the input, we have moved to the alignment. In the alignment, we cannot add two floating point numbers if their exponents are different. For example, 5.75 has an exponent of 2 raised to 2 power, while 2.5 is have the 2.1 power. To fix this, the control logic identifies the smaller number and the shifts its mantissa to the right until the exponent match. Like in this screen, we have visible to align the exponent, and the small you can see the green cubes. You can see the green cubes of the second numbers shifting visually to align with the first. And then the next step is the add the two float numbers called the mantissa addition. In the third step, that the exponent are identical, the aligned mantissas are sent to the integer ALU, and the ALU performs a standard binary addition. In my simulation, the green and blue cubes represent the raw sum dropping into the pipeline. At this stage, we often encounter an overflow where the sum creates an extra bit, like this extra bit, and moving the decimal point out of its standard position. And now we have moved to the step number 4, the normalization. The normalization is a scientific notation, requires exactly 1 before the decimal point. If our addition resulted into something like 10.001, and the system must shift the mantissa and adjust the exponent. In the normalize, we have to see the adjust the exponent, and according to return it to the 1.000 format. The 3D cubes move again to show this corrective shift, ensuring the results is mathematically valid for the next operation. And the step number 5 is the rounding operation. In the rounding, because hardware register have fixed widths in this case, So 6 bits for the mantissa, we must truncate or round any extra bits generated, generated during addition. You will notice the trailing cubes fading out. This signifies that the extra precision is being dropped to fit the memory constraints. This concludes the pipeline, and the final results is now ready to be stored. We have seen the final results in the pipeline monitor, and we have seen all the steps in the pipeline monitor with normalization, like add operation, align operation, and input.